Hi Pre-Cal scholars. In this video lesson we're going to talk about our section 3C notes. We're going to start talking about zeros of polynomial functions. Remember that when we talk about zeros of polynomials, what we're talking about are x-intercepts. So what we are looking for are the x-intercepts of our polynomial function, or we're looking for solutions to the equation f of x equals 0. Remember that some of those zeros, some of the solutions to f of x equals 0 won't show up as x-intercepts because some equations will have non-real or imaginary roots. And we know we've seen cases like that back when we learned about quadratics in Math 2. We learned that a quadratic like this that doesn't pass through the x-axis at all still has two roots. All quadratics, all degree 2 polynomials should have two roots. But cases like this, those roots would be imaginary. They would be non-real. We're going to use 3 theorems to help us find these zeros. The first 2 have to do with remainders when we perform division on polynomial functions. So we're going to start with something called the remainder theorem. So the remainder theorem says if f of x is divided by the binomial x minus k, the remainder is f of k. Which is actually kind of cool. So that means I can figure out remainders when I'm dividing by a binomial without having to do division. We're going to check with an example. So we're going to do f of x equals, 6x to the 4th minus x cubed minus 15x squared plus 2x minus 7. And I'm going to take f of x and I'm going to divide it by x minus 2. So what I expect, if the remainder theorem is true, is I expect that my remainder, when I do long division or synthetic division, should be equal to f of k. And notice in our remainder theorem, it's x minus k. The minus is built in, so the sign on k changes. Minus is built in, sign on k changes. So this should be positive 2. So I expect my remainder is going to be f of 2. Let's find that really quick and then verify through synthetic division. So f of 2 would be 6, 2 to the 4th, minus 2 cubed, minus 15 times 2 squared, plus 2 times 2 minus 7. And I'm going to go ahead and plug that in our calculator. Notice this looks exactly like I wrote it on the paper. When in doubt, that's the best method to evaluate stuff in your calculator. And I'm going to press enter and we get 25. So my expectation when I perform synthetic division is that I'm going to get a remainder of 25. So let's go ahead and do that synthetic division. I know that the k, which is 2, goes out in front. And then I'm going to write the coefficients of the polynomial. And looking at f of x, I don't see any missing terms. Fourth, third, second, linear constant. So I'm just going to write those coefficients. X, -1, -15, +2, -7. And I know it's always that last section that gives me the remainder. So my remainder should show up here. So I start by bringing down the 6, and then I multiply, write the result here, and add down. So 2 times 6 is 12, -1 plus 12 is 11, 2 times 11 is 22, -15 plus 22 is 7, 2 times 7 is 14, yes, 2 plus 14 is 16, and 2 times 16 is 32, and -7 plus 32 is 25. So our remainder theorem checks out. So this is super duper important. This is going to help us identify zeros of our polynomial. The next thing we're going to talk about is called the factor theorem. And I think the factor theorem is a little bit of common sense when it comes to division. What the factor theorem says is that k is a zero of our polynomial f of x. Oops. If and only if x minus k is a factor of f of x. And what that means when we say something is a factor of f of x, that means that my remainder should be 0. So that means f of x divided by x minus k has a remainder of 0. And we know from our previous theorem, the remainder theorem, that that means that f of k should be 0. So super helpful theorem. So let's go ahead and use our new factor theorem to find all of the zeros of a polynomial. So for this example, we want to find the zeros of f of x equals x cubed plus 4x squared minus 4x minus 16, given that x minus 2 is a factor. So that does two things for me. First, I already know one of my zeros. I know that I have a zero where I have a factor. So k is a zero of my polynomial because x minus k is a factor. That's what the factor theorem tells me. I can find the rest by dividing out the factor I'm given and then factoring the polynomial that's left. Because this is cubic, if I divide it by x to the minus 2, I should end up with a quadratic, and I can probably factor that. So first, x minus 2 is a factor, tells me that x equals 2 is a 0. And when I perform division, I should get 0 as a remainder. So let's go ahead and do synthetic division to reduce this polynomial. Let's divide out that factor. So k is equal to 2. The coefficients of my polynomial are 1, 4, -4, and -16. And I know that that last box should give me my remainder. I bring down the leading coefficient of 1. 2 times 1 is 1. 4 plus 1 is 5. 2 times 5 is 10. -4 plus 10 is -6. Is that right? Did I do something wrong? Why do I feel like I did something wrong? 2 times -6 is not -16. Uh-oh. Uh-oh. Did Mr. Jolliffe make a boo-boo? That can't be right. 2 times... Oh, I did make a boo-boo, and I didn't have anyone here to catch me. 2 times 1 is 2. Ha! 4 plus 2 is 6. 2 times 6 is 12. 12 minus 4 is 8. 2 times 8 is 16. There we go. That's what happens when I don't have you here to catch me in my nonsense. This checks out. We knew we should have gotten a remainder of 0. And I know these are now the coefficients on my reduced polynomial. So x squared plus 6x plus 8. And this is something I know is factorable. So I'm looking for factors of 8 that add to 6, and I know that that's 2 and 4. So this is x plus 2 times x plus 4. And that's going to give me 2 additional zeros. X plus 2 equals 0 gives me the 0, x equals -2. And x plus 4 equals 0 gives me the 0, x equals -4. So the zeros of f of x are x equals -4, -2, and 2. I'm writing them in order as they appear on the number line. In our next video, we're going to talk about the last theorem for this section, which is called the rational zero theorem, which helps us guess what our possible zeros will look like. And then we can use synthetic division to pick off the ones that are actually zeros, and then reduce our polynomial down to something that's factorable. If you have questions on anything you saw in this video, feel free to send me an email. Otherwise, I'll be back on campus on Wednesday, and you can check in with me then.